we have plotted this Q versus delta curve. Okay. So depending on the demand and capacity ratio, we have located different plastic hinges. So we have found out the sequence of formation of the plastic hinges. Then we have seen that as and when a plastic hinge forms, the stiffness reduces. Okay, and we can perform a piecewise linear analysis to get this Q versus delta curve. Okay, this curve is also called pushover curve or capacity curve. So this is capacity curve. And what it is representing? It is representing stiffness, strength, and ductility of the structure. So this capacity curve represents three properties: stiffness, strength, and ductility. Okay, this is the simplest structure but hypothetical. Okay, where we have assumed the beams to be infinitely rigid. In real structures, beams will never be infinitely rigid. Okay. In the tutorial, you can have a look at tutorial number 2. I have asked you to do it for multi-story building with multiple bays also. Let's say this is Q and this is 2Q. So this ratio at the two floors, this is important. So what does that mean? That when this force is Q, this force here will be 2. This ratio needs to be known. Okay, then only you can solve it. Otherwise, if both loads are different, there are two unknowns, then it is difficult to solve. Okay, and then the total force will be given by base shear, that will be equal to 3. Now, what will you do when you tally the steps? In the same way it is to be done as we have done earlier. What will be the difference? First, under Q and 2Q, you will calculate the bending moment demand in every member. Can you calculate? Let's do for this case, okay, where all, for simplicity, I am considering all these capacities as equal. Let me number these potential hinge locations as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 12 plastic hinge locations are there. Potential plastic hinge locations where plastic hinges can form. In beams, we are not considering the possibility of formation of the plastic hinge because we are assuming those to be infinitely rigid and infinitely strong. So the hinges will form in columns and the capacity is equal. Let us say all the columns are having same moment capacity. Okay, and it is subjected to lateral load. We know that the lateral load acting at the top will be higher than acting at the first load. That we know from our first semester. Okay, but how much will be the ratio of the two? That will depend on contribution of different modes, okay, and mode shapes. So this ratio may vary. Not only it will vary from building to building, within the same building, this will vary. Why it will vary within the same building? Because when the yielding will occur, plastic hinges will form, the stiffness of the structure will change, okay, its mode shape is going to change. So mode shape will not remain same throughout, mode shape itself will change. So the distribution along the height is also going to be different at different instants of time. Usually what we do, we assume that it is proportional to the first elastic mode. So we will calculate the mode shape in the elastic condition and we will take the variation proportional to that. Here we have assumed that the mode is linear, let us say this is Q, so this will be 2Q. Okay. Can you calculate the demand at different locations? So if this is Q and 2Q, can you calculate M1, M2, M3, M4? So can you calculate? Please do that. All columns have equal EI and equal moment density. Let's first do that. So can you calculate M1, M2, M3, M4, M5, M6, M7? Is it determinate or indeterminate structure? Yes? Speak clearly, I am not able to understand what you are saying. Indeterminate. Indeterminate. So indeterminate structure, can you calculate the demand directly? No, you have to use compatibility condition. You can't solve it without using compatibility condition. So what is the compatibility condition here? The displacement of all the columns connected here is going to be the same. So let us say this is delta 1 and this is delta 2. So delta 1 for all the columns will be same and delta 2 for all the columns will be same. So that is our compatibility. And second compatibility condition is that this angle here, this will remain 90 degrees. So this slab, this beams which are infinitely rigid, okay, those will remain horizontal. So the tangent at the top and bottom of all the columns is going to be vertical. Okay, that means the point of counterfraction will be in the middle. So you can assume that point of counterfraction in the middle and the displacement is same. Using these two conditions, now you can solve it. These conditions are coming from compatibility. So the displacement of all the columns is equal. What does that give us? If the displacement is same, what will happen? It means that the shear force in different columns will be divided in proportion to their stiffness. Displacement is same, shear force is stiffness K into delta. Okay, so delta is same, so the shear force will be divided in proportion to stiffness. And here stiffness is same because EI and L is same, so that means the force will be same. So force In the top story columns, all top story columns will be same, force on all bottom story columns will be same. So how much will be the force in each bottom story column?
Q by 3.
Q by 3? Everybody agrees? Q by 3? Yes? Everybody agrees it will be Q by 3? Anybody having doubt? It will be Q by 3 or Q? What will happen to that 2Q which is applied at the top? Where will it go? How it will be transferred to the ground? So 2Q is acting here. This 2Q, if you show it, this 2Q is divided here. But whatever is this force, equal and opposite of that will also be applied here. So the force here or the story shear will be 3Q, not Q. Whatever is acting 2Q in the second story, that will also be transferred to the bottom story. That's how it will flow to the ground. Because finally, all this load has to be transferred here. So it is the story shear which will be divided in columns, not the floor load. So story shear in the ground story is 3Q. Okay. So how much will be the force in each column? Q. So force is Q. There is point of contact fraction at mid height. So how much will be the moment at the two ends?
Q plus by 4.
Let us say this is H and H. So M1 will be QH by 2. M2 will be QH by 2. How much will be M3? How much will be MC? So how much will be that? What's the difference? 2H by 2H by 3. So where the hinge will form, and same will be in M5 and M9, M6 and M10, M7, M11, M8 and M12.
Can you explain QH by 3?
Okay. So how much is the force here in this column? This 2Q will be divided into 3 columns. So how much will be the force in each column? 2Q by 3. And then how much will be the moment? 2Q by 3 into H by 2. Do that. How much do you get? Yes. At the joint. Middle joint you mean 3. 3. Huh. How many members are meeting there at that joint? Rigid beam will not carry any moment. Is this statement correct? It won't deflect, okay, but it will carry moment In fact, it can carry lot of moment. It is infinitely rigid, and that's why I added infinitely strong also. So infinitely rigid being will carry infinite. It can attract infinite large moment, and it can carry, or you should have strength also to resist that moment. Okay, so that unbalanced moment will be taken care of by the beam. It will go to the beam. If beam was not here, or beam was very flexible, then the joint has floated. Okay, so can you tell me where the hinges will form? Calculate DCR at all these points and check where the DCR is maximum. And can you plot base shear versus displacement diagram? Yes. Because this 2Q, any force acting on the building has to finally to be transferred to the ground. Okay, so this 2Q, how it will be transferred to the ground? From these columns, it will be first transferred to this floor, first floor. Then at first floor, there will be Q acting on this floor itself, plus 2Q, which will be coming from the top. So the actual force will be here 3Q, not Q. So 3Q divided by 3, that will be Q. That's why when we are designing the columns, we are not designing for the floor load. We are designing for story shear. So story shear is important. That's why we plot story shear. So it is the story shear which will be registered by the columns, not only floor load. So whatever floor loads are applied above that level, those will also be registered by the columns of that particular story. So can you tell me where you are getting the maximum DCR? Yes. Sorry? Base column. So ground story columns at both the ends you are getting same. So the hinges in the ground story columns will become or will form simultaneously. So what will be our revised structure after formation of these hinges? Now what will be the remaining capacity after first iteration, it will be 0 here, 0 here, m by 3. How did you get m by 3? Earlier it was m here. Okay, so how you have got m by 3? Can you explain? How did you get m by 3 here? Can everybody calculate how much is the balance capacity? Yes. Right. So for obtaining this, first you have to calculate the moment demand at end of step 1. That you should calculate. So how much is that? At location 1, 2, 3, and 4. After step 1 means you have equated the maximum DCR in step 1 equal to 1. Then you will get the value of Q in terms of M. Okay? Then substitute that value of Q in terms of M in M1, M2, M3, M4. So from here, by equating QH by 2 equal to M, you will get Q in terms of M. Okay, substitute that value here. Then you will get M1, M2, M3, M4. That is the moment demand at end of step 1. So please do calculate. Q will be 2m by h, and m1 was 2h by 3. Okay. 2qh by 3 substitute q as 2m by h. 2m by h, 2h by 2. Q is 2m by h, h by 2. So how much is that? 2m. So it is 2m by 2. Balance is that. Right.
At 4 points.
Right.
जब DCR निकाला तो QH by 2 mm साथ ही है। तो सबसे मेजर DCR और DCR 2 आया तो उधर हिंज जाएगी।
राइट राइट, उसको हम 1 इक्वेट करेंगे।
डिमांड
अब इसको हिंज कब बनेगा? जब ये 1 होगा, तो तो इसको 1 इक्वेट करके, जो मैक्सिमम वाला वैल्यू है उसको 1 इक्वेट करके यू कैलकुलेट Q इन टर्म्स ऑफ M.
2h by q.
2h by
Q in terms of M.
2m by h.
You put this equal to 1, QH by 2M equal to 1, write down, and then you calculate Q
2m by h.
2M by H. Now substitute this Q in all of these. So follow all the steps, do not skip anything. So M1, M2, M3 we have calculated, then you calculate DCR. Okay, and whatever is the maximum DCR, you equate that equal to 1, and then you will get Q in terms of M as a function of M, you get. And then substitute it here. That will give you the demand at the end of step 1. So please do that, everybody. Okay. So what will be the balance? The balance capacity remaining after step 1 from the original capacity, you subtract the demand at the end of step 1. So this will be at point 1, this will be M minus M 0. At point 2, it will be M minus M 0. At point 3, M minus 2 by 3M is equal to M by 3. And at point 4, this will be M minus 2 by 3M equal to M by 3. So this will be 0 and 3 Can you plot the deformed shape now? for this second step, second increment of the load, can you plot the deformation? Sorry? Yes, we have to find it out. I have not yet found it out, but you can find it out. Can you plot the deformation for this structure? Right? First of all, tell me, is it a structure or mechanism? Mechanism. What is the difference between a structure and mechanism? Yes? What is the difference between a structure and a mechanism? It is deforming without force. Then it is called mechanism. Okay. So here, since the plastic hinges are formed here, it can't take any load. Because if you apply any load at the top floor, let us say, what will happen to that load? These columns can resist. But the bottom story cannot resist any load. So you can't apply any load neither at the top floor nor at the bottom. Okay. Without load itself, it will deform. Or whatever load was there in step 1, under that load itself, it will continue to deform. Okay. So in step 2, there will not be any load, but still it will be deforming. So the bottom story columns without any load, no bending moment, so those will remain straight. Okay. The upper story columns, no load. So how those will be deformed? Those will remain vertical. Okay. There is no load, so those are not going to deform. Those can't bend. Okay. So no bending. So the deformed shape will be like this. So the second story will just slide above the first story. The deformations will occur in first story only, because that is forming a mechanism. There the deformation can occur without load. But second story is still intact. Okay. So there, if no force, no deformation. So that's why the interstory drift which is occurring in the second story will be 0. So whatever is the deformation of the base of the second story, that will be the deformation of the top of the second story. Okay?
Sir,
Yes.
so here the first story can't move like rigid rotation because
First story can't move.
rigid rotation like this.
No, sorry, I couldn't get. Why can't it move? Rotation can occur. Plastic rotation can occur.
But because 2Q is also acting on the first floor. No?
Actually, no 2Q can act because it can move without any load. If you apply any force here, what will happen? The same force will be applied here also. Suppose I apply load only at the top story. Let's consider this structure. Subjected to a load here, Q. What will happen? The same Q, if you plot the story shear, here the story shear will be Q, here also the story shear will be Q. So this will also be Q, V1, that will also be Q, V2 will also be Q. But other way around I have written. This is V1, this is V2. So both are Q. But first story cannot take any shear. It is having hinges at both the ends. So it can't take any load. So this has to be equal to 0. That means Q has to be 0. You agree? So we can't apply any force even at that story. Doesn't mean that this story is intact, so I can apply a force at the top of that. You have to see the full flow of the load, how it will reach ground. Okay? So because there is a story below which can't take any load, so this story will also not have any load. Okay? And if there is no load, there will not be any deformation in this story. But the ground story can deform even without load. That's how you define mechanism. So this can move without any load. And this will remain vertical. The columns in the second story will remain vertical because there is no load. Yes. 0 incremental load. After study. This is not overload. In this, the previous deflected shape is to be added. Okay? So when you will be plotting VV versus delta roof. Okay? Earlier you have plotted Q versus delta. There was only one Q. Here there are two forces, Q and 2Q. So which one we will take? Base shear, sum of all those. Similarly, the displacement is also at two levels, delta 1 and delta 2. Which one we should consider? You can consider any, it's your choice. But the natural choice is the maximum which is applied at the roof. So here we will be plotting the graph between base shear and delta roof. Okay, so for step 1, you have already calculated the base shear. How much was the base shear in step 1? 3Q, but Q you have calculated in terms of M. Q is a variable.
6 by H.
6 M by H. What is the corresponding roof displacement? Calculate the corresponding roof displacement at the end of step 1. Calculate delta 1, okay, and then delta 2. Delta 2 will consist of delta 1 plus the deformation in second story. So if I calculate displacement here, delta 1 will be equal to, displacement of all the columns is equal at first floor level. So I can calculate for one column. In one column, force was how much?
2Q by 3.
2Q by 3. Okay. So, and then how much will be delta in terms of Q? Whatever is the shear force, okay, if it is a fixed beam, what is the displacement?
PL2 by 3I.
No, that is for cantilever.
We will cut in 2 pieces.
You can cut it into 2 pieces, or you can also write for this case. What is the relationship between V and delta? V is equal to so delta is how much? Substitute V as 2Q by 3. That's what you have calculated. And Q you substitute in terms of M. Bottom floor Q by 3. So bottom delta 1 is in the bottom. In bottom floor, how much was the shear force in bottom floor? Q. It was Q1. No? So delta 1 is Q LQ over 12 EL. Q you substitute in terms of M. You have calculated Q in terms of M. How much was that? Q is Q was how much? 2M by H. So this will become 2M HQ by H into 12 EL. So that will be mh square over 6L. That is delta 1.
This is for whole story, not for one.
For whole story it is same. Displacement for all the columns is same. So if you calculate for one column, it will be for the whole story. So force is to be added, but displacement is not to be added. Don't add displacement of one column with the other column. Displacement is same.
So your answer will become same if I take Q by 3 as a Q.
Q by 3.
Q as a Q, B as a Q by 3 for one column, if I get correct.
I have done for one column only. But for one column, the force is Q, not Q by 3. How much was the force? You have just determined while calculating moment. How much the force in one column? Shear force in one column was how much? It was not Q by 3, it was Q. The same force which is causing moment, that will cause displacement, no? So you make a free body diagram. This is flow. This is second story column. Then we have flow. Then we have ground story column. Let's make the free body diagram. The force acting here is 2Q. Here it is Q. So how this force is being transferred? From this 2Q, it is 2Q by 3, 2Q by 3, 2Q by 3 going to these columns. From these columns, where it will go? So equal and opposite will act here, and then it will be transferred to this floor. Okay? This will be then how much will be the force here? This 2Q by 3, 2Q by 3, 2Q by 3 plus Q. So how much will be that? 3Q divided into 3. So this will be Q, Q, Q. So deflection of this column, when this column is going to deflect, under which load it is going to deflect? Q, not Q by 3. So this should be clear in your mind. So you have calculated delta 1, okay? Can you calculate delta 2? Delta 2 will be delta 1 plus whatever displacement has occurred in the ground story plus whatever displacement is occurring in the second story. Or you can also write delta 2 minus delta 1 is equal to VL cube over 12VI of second story. In second story, how much was V in one column? 2Q by 3 into now substitute Q as 2m by h as we have done there. So this will be 2 into 2m by 3h into h cube over 12vi. Okay, so that is mh cube over 9. Sorry, mh square over 9. Am I right? So how much will be delta 2 then? That will be delta 1 plus mh square over 9ei. Delta 1 we have calculated mh square over 6ei. So 5 mh square over 15. This is our delta. It will become flat. Previous slide. This one. Yes.
पहले केस में यहाँ पे शेयर फोर्स जीरो लिया, यहाँ से यहाँ पे अगर मैं ये सब कंसिडर करूँ,
ऐसा
इसे बीम कंसिडर करूँ,
हाँ
यहाँ पे फोर्स लगा तो यहाँ पे हिंज लगा तो यहाँ से तो यहाँ पे शेयर फोर्स ट्रांसफर होगा,
कहाँ से कहाँ तक ट्रांसफर होगा?
यहाँ से यहाँ पे जैसे ये पी है, यहाँ पे शेयर फोर्स आएगा, ये ट्रांसफर तो होगा यहाँ।
कैसे ट्रांसफर होगा?
ये आप बताओ।
ये तो मैकेनिज्म है, ऐसा लोड लगा के यहाँ से जैसे आप
ये बैंड से
पोस्ट ट्रांसफर कहाँ होगा? हालांकि आपका केस ये वाला नहीं है, आपका केस तो ये वाला है। यहाँ भी है, यहाँ भी और फिर आप इसमें तो बिल्कुल ही नहीं होगा, इसमें भी नहीं।
ऐसे जाएगा
नहीं, ये ऐसे जाएगा और ये कॉन्स्टेंट, क्योंकि फोर्स तो जीरो है। Suppose the rotational ductility of the columns is 4. So if we take mu theta of the columns equal to 4, what will be this delta? Delta u. Rotational ductility is there, and I am asking you to get the displacement. So what you will do? First you will calculate the rotation, chord rotation of the columns, okay, at first heat, where the hinges are formed in the ground stroke. So what was the chord rotation at that time? MH over 6A. How did you calculate? So theta y of the ground story columns, that is delta 1 over h. How much is that? Delta 1 we have calculated earlier, mh square over 6ai. So divided by h, mh over 6a. And then you can calculate theta u1 as 4 times of this. So that will be 4 mh over 6ai, that is 2 by 3 mh over e. Agreed? Then you can calculate delta u1 will be how much? Theta u1 into h, so that is 2 by 3 mh square over e. Now tell me how much will be delta u? If the first story is 2 by 3 mh square, how much will be delta u?
Sir, delta u1 equal to delta y1 plus theta u1 into h.
Sorry?
Delta u1
Delta u1
equal to delta y1 plus theta u1 into h.
So why?
Where
So mu theta is not mu p. So this mu theta is equal to theta u divided by theta y. So theta u is mu theta into theta y, not plus. Ductility ratio I have given, not plastic rotation. If I have given plastic rotation, then you will add that to the yield rotation. But ductility ratio is the ratio of theta u to theta 1. So I have simply multiplied this by 4. So can you tell me delta u then? That will be 2 by 3 mh square over EI plus how much? 5 by what is that? So we'll be adding delta 1 plus delta 2. We will add the displacement of second story. So delta 2 minus delta 1, which we have obtained earlier. We obtained, and that will remain same because in second step, second story will not deform anymore. Whatever displacement was there in the second story, mh square over 9 EI, that will continue the same. Okay, because we have seen here, second story is not changing. Okay, so it will remain same. Plus mh square over 9 EI. How much is that? 2 by 3, so this will be 6 plus 7. 7 by 9. So this will continue up to 7 by 9. The common mistake I would have done, I would have multiplied this by 4. So it's not. The how much is mu delta for this structure? Delta u divided by delta y. So how much is that? So 14 by 5. Roughly so you can see that the rotational ductility was 4 for individual column, but the displacement ductility for the structure has reduced. That is 3. So what we did, from strain ductility we calculated curvature ductility. From curvature ductility we calculated rotation ductility. From rotation ductility we have calculated structural ductility or displacement ductility. The strain ductility is also called what? I have told you? Material ductility. Curvature ductility is section ductility. So curvature ductility depends on the section property. Okay, which requires material and its placement. It does not require length of the member. Okay, then rotational ductility is member ductility. It requires only member property. And then displacement ductility requires whole configuration of the structure. It depends on the structural configuration. So when the structural configuration changes, the displacement ductility will change.
Sir,
Yes.
this whatever the chart we are plotting here with respect to delta top and base ratio.
Yes, that's what we have decided. We have decided here that we will be plotting base shear versus delta. And why we decided so? Because there are two forces. So which one we should take? That was the question. So we decided that we will take the total force which is acting on the structure, and total force is given by base shear. Then there were two displacements. So there was a question, which displacement should I take? So we decided that we will take the maximum displacement. Where is the maximum displacement occurring? At the top. So that's why we have plotted with respect to delta. Now have a look at in your tutorial sheet how many questions now you can do. There should not be any tutorial. You decide that. I will ask no problem. So how many questions you can do now? Tutorial number 2. अरे पीछे से स्टार्ट कर लो, फ्रंट से स्टार्ट कर लो भाई, पीछे से तो वैसे ही नहीं पता चलेगा. How many questions you can do? First time? Yes. How many questions you can do now?
Sir,
Yes.
ये दो डायरेक्शन में क्यों क्यों लगे?
Right. So, earthquake force can be towards left, it can be towards right also. So, will there be any change if I change the direction of the force?
Yes.
Suppose I apply the force in the opposite direction. Will there be any change in the load versus displacement curve? Not in this case. Okay. But in some structures, we will see later if the capacity of a beam in hogging and sagging is different. Okay. Then there may be change also. In this case, there you will not find any change.
If EI changes, then
No. If EI of different columns is different, then it is not good.
if this would be EI, and this would be
Whatever. Then direction. You will think. Okay. You think and try. So I want you to think in this assignment, I have tried to give you different situations. You can think more situations yourself. Definitely in exam, it will be different than whatever is given in this. So you think about other situations, what can happen. But with these questions, you will have a fair idea. Yes, so is there anybody who can do more than one question? Second वाला करेंगे? Who said? Yes. You can do second? Okay. So please do the second question. Very good. So AK Chopra you can find, somebody may be having it. Do that.
इसमें मार्केटिंग मारने को
With that, okay. So extend that.
इस वाले केस में हमने मूवमेंट निकाल के प्लास्टिक इंच फॉर्म कर रहे थे हर एक जगह पे
ऐसे इसमें करो.
इस वाले केस में पूरे
Procedure will remain same. Whatever is the structure, the steps remain same. First you perform a linear analysis, calculate demand, then calculate demand to capacity ratio. Wherever the demand to capacity ratio is maximum, you equate that equal to 1. Then at that stage, you calculate the displacement and forces in different manner. Then you go to the next step. From the original capacity, you remove, you subtract the demand at the end of first step. So that will be your balanced capacity or remaining capacity. Remaining capacity you will assign. Again, you will perform a linear analysis of the new structure, which is there in step 2. And there you have assigned a relief wherever the hinges are formed. Okay, continue that. So the procedure will remain same for all structures. So let's consider this case. Now we will go to the real building. Okay. So far we have done simplified structure. First we did cantilever, then we have taken simply supported beam, either subjected to a load at the center or subjected to two equal and opposite moments. We have done fixed column, and then we did a hypothetical frame which has infinitely rigid and strong beams, which is hypothetical. In real building, the beams are not infinitely rigid. Same problem, but the beams are not infinitely rigid. What will happen now? Can you plot the deformed shape? Please plot the deformed shape. This we have done in the last semester also. So try to plot the deformed shape. Under these vector rows. None of the members is infinitely rigid. Let us say this as EIC, EIC, EIC. The columns are identical and all the beams are also identical. So how the deformed shape will look like? Please plot. Sorry? Actually, you can assume rigid because it is only a two-story building. So actual deformations will be very small. So actually, you can consider those as rigid. Okay, you can ignore rather actual deformations. It is not actually rigid, but actual deformations we can ignore. If it was a very tall building, 20th story or 40th story, we can't ignore actual deformation. But in a two-story building, we can ignore actual deformation and then plot the deformation. To check what I told, you should see where, in which side the tension is occurring and which side the rotation is occurring. That you should see. So every joint can now rotate. Earlier beams were rigid, so joints were not rotating. Now the joints can rotate. So show the rotation of the joint, in which direction those are rotating, and then you have to check compression and tension phases of beam and column. It should be in equilibrium. Like this. First plot, consider this as single story plot here, and then you can plot this. First plot, single story single way, which we have done in the last one. So let's first plot for this. That will give you idea. So we discussed that let's assume first that there is no connection between beams and columns. So our columns are going to deform like this. Okay, so the joint is rotating here. But the beams and columns are rigid. So whatever is the rotation, same rotation has to be in the beam also. So that is possible if the beam is rotating like this. This end has to rotate left, this end has to, both the ends will rotate like this. Then I told you that since the tension is here the tension is here. So for equilibrium, if the tension is inside in the beam, the tension will be inside in the column also. If the tension is outside in the beam, it will be outside in the column. So this is going to be formed like this, and this is going to be formed like this. Now you can extend this to this. So okay. Agreed? What I wanted was to locate the points of contraflexion. To locate the points of contraflexion, where the points of contraflexion are there. Point of contraflexion means bending in opposite direction. So the direction of bending is changing. Contra means opposite, flexion means bending. So the bending is opposite. So here the bending is in this direction, here the bending is in this direction. Similarly here the bending is in this direction, whereas here the bending is in this direction. So points of contraflexion are here, 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 you agree? These are our points of contraflexion, where the bending moment is 0, because the bending moment is changing sign. If I want to plot the bending moment diagram, how the bending moment diagram will look like? Let me use another color. So bending moment diagram, we are plotting on the tension phase. So you can see that tension is at the bottom and here it is at the top. Okay. Then here the tension is at the bottom, here it is at the top. Okay. Here it is inside and here it is outside. So this is a typical bending moment diagram and deflected shade under lateral lobes. And you can see that point of contraflexion is occurring somewhere in the middle of the beam and in the middle of the column. But it may not occur exactly at the middle of the column. Why? In which case it will occur exactly at the middle of the column? If the stiffness at the two ends, the rotational restraint at the two ends is equal. Okay? But you can see that the rotational restraint at the two ends may not be equal. Here, this beam is restraining two columns. Here, this beam is restraining only one column. Okay? Here, this column is being restrained by two beams. Here, this column is being restrained by one beam. Okay? So the stiffness at the two ends is not exactly equal. So point of contraflexion will not be exactly in the middle. Okay, you can plot the bending moment diagram and see points of contraflexion will not be exactly in the middle. But we will make an assumption because we want to do hand calculation. We want to simplify. It is a indeterminate structure. Okay, indeterminate structure we can't solve. It's manual. Okay, we have to solve. We have to take into account compatibility condition, or we have to simplify something. So we will make an assumption, and that assumption is that we will consider points of counterflexure in the middle of the members, at the mid height of the columns and mid span of the beams. We will consider our points of counterflexure here. This assumption we will make. When you will be doing analysis using a computer, you need not to make this assumption. This assumption we are making only because we want to analyze using manual calculation. We want to simplify the calculation. So for simplification of the calculations, we are making this assumption. But it is not necessary to always make this assumption. You can analyze the actual structure using a computer where you can consider the stiffness, actual stiffness of different members, and automatically point of counterflexure will be considered. And then what we do, we can divide, we can assume that here there are hinges, physical hinges, releases. Can I do that? Will the behavior of this structure be same as of this structure? What do you think? Do you agree? Behavior of this structure is same as this structure. Everybody agrees? Anybody having doubt? Hey, do not just accept because I am saying. So wherever the moment is zero, why I need to transfer the moment? Why I should provide capacity to resist moment there? Moment in any case is zero there. So I can provide these releases there. You agree?
Can we close the force transformation at VD?
Sorry?
At VD with that this at
FVD. Free body diagram. Yeah, that we will show you. We will show you. Free body diagram. We will show you. We will show free body diagram. So what we will do, this structure we will divide into some sub-assemblies like this one, this and this are same. And then so I have divided the whole structure into different sub-assemblies. Let us say the center one, this is of type 1. What is this? This is having a cross. This is one. Okay. Then this assembly is connected with other assemblies. How it is connected? Through shear. No moment, but shear transfer. So shear transfer can take place here, but no moment transfer. Okay. Similarly, this one, let's take type 2. So here also the shear transfer can take place, but no moment transfer. This is also of type 2, you agree? It is just reverse of that. And then this is type 3. The third type of assembly will be this, which can again be in equilibrium under these three shear forces. Okay, and then this is type 4, this and this. Type 4, where we have column and beam.
Sir, but the transfer of shear force is happening because of the changing bending moment along that span. So we are considering also moment there while considering shear force.
Sorry, I couldn't get. What are you saying?
If I am taking this beam, some element is there. And
Right.
from this part to this part, some shear force is transferring.
Right.
This is due to the tending moment from this section to this section.
Right.
Then I am considering, if I am considering shear forces over there, then I am also considering the moment transferring from.
No, we are not considering moment. Shear is rate of change of moment, not equal to moment. So when moment is 0, is its rate of change 0?
No.
No. So rate of change of moment is there even at point of contact. Value is 0, but moment is changing sign. One thing also I forgot, that at this hinge, not only shear but axial force can also be transferred. Okay, so in addition to shear force, axial forces can also act. Because otherwise this can't be in equilibrium. This fourth one won't be in equilibrium if axial force was not there. So we have axial forces. Under these, it can also be. And then it may also be subjected to a force. And the last one, last assembly type is this cantilever, which you are very familiar. All these are of type 5. Just a cantilever subjected to a shear force and action force. So these 5 types of assemblies, using these 5 types of assemblies, you can define the whole frame of n number of stories and m number of bays. So any size of the frame you can define with these 5 types of subassemblies. Okay. So let us consider their behavior one by one. Can we plot the capacity curve of these individual assemblies, and then we can combine those assemblies in parallel and series. For example, assembly number 2 and assembly number 5. How those are connected? In parallel or series? Or let's first take these assemblies. 1 and 2. How these are connected? Displacement between two floors will remain same. Okay. So actually between this floor and this floor it will remain same. We are assuming that between this and this also it is same. We are considering these our connections, our releases at mid height. So it is not floor to floor, but mid height of the story to mid height. We are considering. Okay. So you can see that these are all in parallel. These all are in parallel. These all are in parallel. And then these stories, different stories, are in series. So if we can calculate the load versus displacement response or capacity curve of individual assemblies, we can combine those in series and parallel to get the capacity curve of the whole. Okay. That's what we are going to do.
Sir,
Yeah.
repeat how to decide series and parallel.
Okay. So it's simple. You are very familiar with this example. Which one is in series?
Below.
Below. Why you say it is in series? Because one is ahead of the other.
Now, the displacement, when I put displacement here, it will not be equal. It will depend on the stiffness of individuals.
So in this case, the force will be equal. So the force will be equal. Okay. If no force is acting in between, suppose I apply a force here, then what will happen? Then force is no more equal. But still these are in series. Connection is still in series. Okay. So equilibrium of the forces or transfer of the forces is taking place. Okay. Displacements are not same. Here what is happening? The displacement is going to be the same. So same thing we will consider here. What is happening in all these assemblies which are on a story? The displacement is going to be the same. All will move together. So if displacement is same, it is in
Parallel.
parallel. Now what is happening between story, top story and the bottom story? Whatever force is acting here, same force will be transferred to this. But there is an additional force also coming here. We will see what we'll do with that. Okay. But these are, even if this force is there or it is not there, the connection is in series. If you will apply a force here, same force will be applied in the story below. Okay. So this will be in series. Alright. So let's first take the first assembly, the simplest one. This is assembly. Let's apply a force Q here. How it will be in equilibrium under this Q? At the bottom, there will be an equal and opposite force. Take it here. I am applying a force here. Then what will happen? It will try to deform,
Yes.
but at the base, this column will hold it. Okay. So this column will also deform, but I am calculating the deformation occurring within this assembly itself. So what can I do? I can replace it with a pin here. Not roller, but pin. Now what is happening here? You go back to the deformed shape. How much is the vertical displacement here?
0.
So the vertical displacement at the points of contraflexion will be 0. In all buildings? Where? In which case? When we have ignored axial deformation of column. Okay, so that means low right. Or we can calculate the axial deformation of the column separately and then we can superpose. Okay. So if we assume that axial force in all the columns is same, cross-sectional area is also same, so axial deformation will be same. Okay. But when it is subjected to lateral load, one side columns are subjected to tension, other side columns are subjected to compression. So for tall buildings that will be significant. We can't ignore it. So this we can do for low rise buildings, for short buildings, where axial deformation in columns is less. There we can do this manual calculation. So what will that mean? That I have to provide okay. Can I provide pins there? Hinge support? No, because it is allowed to move. Okay, it is only prevented to move vertically and the moment is zero. So that means this is not correct. I have to provide rollers here. It is representing the situation of this assembly in the actual flow. Now, Can you plot the deformed shape? What is going to happen here? You have done it in first semester. Top and bottom columns are yes. So this is our assumption that either the point of contraflexure is in the middle or it is known. So point of contraflexure, location of the point of contraflexure is known. Okay, in that one, then only we can use this technique. If the point of contraflexure is not known, we can't. So in our case, we are assuming that the point of contraflexure is known and it is in the middle of the beam. That assumption is there and that will cause some error in our case. We are willing to tolerate, willing to accept that much error. So can you please plot the deformed shape? How this is going to deform? No. Why do bend upward? We are applying load here, so how can it bend back?
Connected with upper building.
Here it is not connected. From here it is only a force Q coming from the top. No moment can come from the top. Because this is point of contraflexion. Here is a pin, release. So no moment can come. Will it remain straight? Is it straight?
No, it's not straight.
So then draw how it looks like. You have rubber. Erase it and draw correctly. How to do it? This suppose explain it. Okay. So look the situation in the actual building. In actual building we are considering this. So what is happening here? If you consider this middle, what is happening here? Here you can see that the vertical displacement is 0, vertical displacement is 0, but translation can occur, horizontal translation can occur. So we have provided roller here. Here this point can move. Okay, but we have provided a pin because we are considering the deformation with respect to this point. So we will calculate only the additional deformation which will occur. Whatever deformation is occurring below that, that is because of this cantilever column that we will add later. Okay, so we are providing a pin. So what is happening at the top? Actually, I have already plotted the deformed shape here. Same deformed shape, we have to translate. Plotted shape is here already. So same shape we will get here. Suppose this beam was not there. There was only column. How it had deformed? A column pinned at the base and free at the top, and I am applying a load. How it will deform? It will remain straight. And it will deform like this. So if this beam was not there, the column would have deformed like this. Okay, but because beam is there, so the beam will remain perpendicular to it. So the beam has to deform like this. Agree? So due to deformation of the beams itself, okay, column has not deformed, column is rigid. Suppose even if you take this column as rigid, okay, still that deformation is occurring. This deformation we will call delta B. Delta B is the displacement due to bending of beam.
Sir,
Yes.
this junction is cast monolithic.
Right.
So
The
that
angle has to be 90 degrees. This angle is 90 degrees. So this should remain 90 degrees. That's why our beam has to rotate like that.
सर तो जंक्शन है वहाँ पर फिक्स एंड कंसिडर मतलब which type of support we should consider?
There is no support here.
What should
There
we
is
consider?
connection.
हाँ,
Connection between beam and column. Connection is not a support. Connection only means that the angle between beam and column cannot change. So angle which is 90 degree earlier will has to remain same.
If I have to plot the bending moment diagram of this vertical member, then it has bending moment diagram like up to this, it will give like this.
Right.
Then here it gets some bending moment. It has to bend.
Right.
Then why it is not bending?
Because I have assumed it to be rigid at the moment. That is my next point. That suppose it is not rigid. Okay. It's interesting, you can plot the bending moment diagram. He has given me a new idea. Can you plot the bending moment diagram? How the bending moment diagram will play in this case? Column is rigid. But again, don't make the same mistake which you have made earlier. Rigid doesn't mean that there will not be bending moment. Rigid means deformation will not be there, but bending moment will be there. So can you plot the bending moment diagram? Plot it on tension phase. So you can see if this is Q, this will also be Q. So bending moment diagram. Due to this, there will be reaction here. Let me call it V. So this V will be how much? Let us say this is L by 2, L by 2, and this is H by 2, H by 2. So how much will be V? Can you calculate? You can take moment about this point or about the center. You can say that V is Q into H divided by N. So the bending moment diagram I am plotting on tension phase. So here it will be like this. And how much is the bending moment here? QH by L into L by 2. So how much will be that? This moment will be QH by 2. Agree? Here the bending moment diagram will be like this. How much will be this moment? QH by 2. Now what will happen in the column? Which side is tension? Left side or right side? Left side? Both? Above and below? Above left? Below? Right. And how much will be this? Agreed? Is the joint in equilibrium? Bend नहीं भी कर रहा है. Let me take this as rigid member. It is not bending, but I apply a force here. Which side will be tension? I am applying force in this direction. So which side will be tension? Is here will be tension, here will be compression. Even if it is not bending, compression and tension will occur. Or even if my structure is very flexible, I apply a small load, deflection will be almost zero. But still I can say which side is tension, which side is compression. Okay, so is it in equilibrium? The joint, you can see, this is clockwise. Okay, and due to this, it is anti-clockwise. So you can see QH by 2, QH by 2 clockwise, QH by 2, QH by 2 anti-clockwise. Sum is 0. Okay. So the joint is in equilibrium. Can you calculate delta V?
Sir,
That this displacement?
repeat after calculation of bending moments at those places. Joint equilibrium.
This you have understood. Now let me consider the forces which are acting at the joint. Let me draw only the joint portion. On this joint, either you can consider the forces applied by the joint on the member or forces applied by the member on the joint. Both ways you can do it. Let us see the forces applied by the member on the joint. So here on right hand side, this force is acting upward.
Yes.
So in which direction the moment will be applied?
Upward.
Upward. How much?
QH by 2.
QH. Left side?
Left side it is down.
Here?
Here it is Q into H by 2.
In which direction?
In this direction.
Here?
QH by 2 in this direction.
What is the summation of M?
0.
Okay, so that's what it is.
Sir,
It should be.
in moment distribution,
Mhm.
we can do that instead of this much calculation, this Q we transfer at the joint Q into H by 2, that moment M equal to Q into H by 2, and we will remove that member, and also
You can use any method.
then we will distribute in terms of
If
strictness.
you are happy with that, you do that. I have no problem with that.
But I have a problem with that what should be the means we have distribution strictness considering another end, that is being around fixed, that is 4 layer wire or being it is 3 layer wire.
You think about it.
But
You are suggesting a new method. It's good, but you have to develop it. Okay, develop it. Think about it wherever, but you try it now first. When you are not able to do it, you come to me. I will help you. Okay, but try it. There is not one way of solving one problem. There are multiple ways of solving one problem. So what we have done, we have used very simple, because after doing all this becomes a determinate structure. In determinate structure, you can solve it easily by equilibrium. So we have just used equilibrium to solve it. Just using equilibrium, we can get all the moments, shear force, axial force, deformation. Okay. So can you tell me how much will be this delta V which is occurring there if I am considering the column to be rigid? This was, let us say, EIG. Okay, other dimensions I am giving you. So how much is the delta V? Let me give you a clue. You can calculate this rotation. Okay, this theta. This theta will be same as this theta. How you can calculate this theta? Same cantilever thing. Treat it as a cantilever, and this force B, what it is doing? It is taking it up. You can calculate this delta. So calculate theta, then delta V will be 2 times theta into h by 2. Agreed? This is theta. This into h by 2 plus this into h by 2. Or you can take this as theta. This is also theta. Okay? And then theta into h. That will give you delta V. You have to calculate theta. Can you calculate theta? Theta is nothing but delta divided by L by 2. And how much is delta? For cantilever? V into L by 2 cube over 3L. 3L. Agree? All this we have done in the first semester. We are repeating that. So in a building, even if we have columns rigid, okay, but pinned at the base, and beams are flexible, still it will undergo lateral deformation. Even if the columns are rigid, beams are flexible. Similarly, we have already seen if the beams are rigid, columns are flexible, then also we have displacement. So lateral displacement will have contribution due to beam as well as due to column. So we are first calculating the contribution of the beam, then we can add into this the contribution of the column. That will be the total displacement. So please carry this on. Okay, try to solve it, and we will discuss when we meet tomorrow at 12.